Good day everyone, we are Group Emerald and today we will be presenting our thermodynamic analysis on the water treatment industry for our chemical engineering thermodynamics course. I will introduce my team members. Me, myself, Nurizati binti Tajuddin. My matric number is 230951. My team members Nurul Aisyatu Alisa binti Muhammad Agus 229852. Balkis binti Manzlan 230626 and Sofia Elia binti Rosli 229022. First, let's look at introductions. What water treatment actually is. At its core, it is the fundamental process of upgrading raw and used water to make it safe, clean and suitable for specific purpose. This requires the systematic removal of various contaminants and hazardous substances. As you can see in our process roadmap, the journey goes from raw water input through three distinct layers. First, separation and purification. Second, the removal of hazardous substance. And third, flow management and control. Our ultimate goal and output is achieving a pristine water supply and meeting zero discharge targets. So, why is water treatment so critical? We can break its importance down into three main pillars. First, public health. It entirely mitigates waterborne disease. Second, resource management. Water is finite, so treating wastewater ensures continuous availability. And third, environmental protection. It ensures the water will return to ecosystem is completely safe. Because of this, the applications are highly diverse. Water treatment isn't just about producing clean drinking water, it's also vital for supplying water tailored for heavy industrial operations, supporting recreational areas, restoring natural ecosystem, and safely processing domestic and industrial wastewater before it returns to the water cycle.
Here are the examples of water treatment plants. The first one shows the Serang Water Treatment Plant in Indonesia, and below are photos of the Batu Kitang plant in Sarawak. Okay, now I'll be explaining the basic process flow of water treatment. Firstly, we start with raw water intake, where water from natural sources like rivers or lakes is collected. Next is coagulation and flocculation. In this step, chemicals are added to help tiny particles stick together and form larger clumps called flocks. Then the water goes through sedimentation, where the flocks settle at the bottom, leaving the clearer water on top. After that, the water passes through filtration or reverse osmosis to remove smaller impurities and dissolved substances. The next stage is disinfection using methods like chlorination or UV light to kill harmful microorganisms. Finally, the clean water is stored in storage tank before being distributed for use.
Now, let's look into the core engineering operations. Starting with process 1, coagulation. In raw water, impurity particles carry negative surface charge that cause them to repel each other, keeping them suspended. The sole purpose of coagulation is to neutralize this electrical charge so the impurities can come together. How does it work? Highly positive coagulants, specifically aluminium sulfate or ferric chloride, are rapidly mixed into the raw water. As a result, these positive coagulant ions attract and wrap around the negatively charged colloidal particles. By neutralizing their surface charge, we eliminate the repulsive electrical fields, destabilizing the particles so they can finally stick together upon contact. Now, let's look at this through a thermodynamic lens, focusing first on energy changes and equilibrium limits. From an energy standpoint, the overall process of coagulation is exothermic, meaning delta H less than 0. Dissolving aluminium or iron salts in water naturally releases heat. Once the electrical repulsion is removed, colloid aggregation happens spontaneously. The particles move from a high energy state to a lower, more stable energy state, minimizing their surface Gibbs energy and releasing thermal energy. Thermodynamically, this transition is governed by Gibbs free energy, delta G. In a stable suspension, repulsion dominates and delta G more than 0, meaning aggregation won't happen. When we add the right dose of coagulant, the energy barrier is removed. delta G become negative, which is delta G is less than 0 and spontaneous flow growth occurs. However, as engineer, we must watch out for conversion limits, as shown in the zeta potential graph. There is an optimal zone, right around 0 millivolt, where charges are perfectly neutralized. If we add an excess dose of coagulant, the particle absorb too many positive ions, restabilize with a net positive charge, and delta G become positive again, which means delta G is more than 0, halting flock formation entirely. To wrap up our thermodynamic analysis of coagulation, let's look at how operating conditions like temperature and pressure affect the process. First, temperature has a significant kinetic and thermodynamic impact. Lower water temperatures increase the absolute viscosity of the fluid, which directly slows down particle collision kinetics. Furthermore, low temperatures slow down the chemical hydrolysis rate of our metal coagulants. This means that in colder conditions, industrial plants require higher chemical doses to achieve the same level of destabilization. Second, pressure has visually no impact. Coagulation strictly involves liquid-solid interaction where the molar volume shifts are negligible, meaning the delta V approximate is 0. Because of this, variation in industrial operating pressure have no measurable thermodynamic effect on the coagulation equilibrium. That's all for the part 1, coagulation process.
Now, we will review the process 2, flocculations. Following the rapid flush mixing phase, the water transitions into a series of flush basins. These basins are equipped with slow-moving mechanical paddles. The primary purpose of this stage is to physically force the neutralized particles to collide, enabling them to aggregate into larger structures known as flocks. In terms of result, the gentle stirring action successfully drives these particles to collide and adhere to one another. To enhance this process, long chain polymers can be introduced. These polymers serve as a physical mesh that binds and reinforces the expanding flocks, protecting them against the disruptive forces of fluid shear currents. Now, let's look at the thermodynamic analysis of the flocculation process broken down into 3 key areas. First, the energy driving this process is entirely mechanical shaft work, derived from external mechanical energy dissipation rather than chemical potentials. This work establishes a controlled fluid velocity gradient defined as the shear rate. Regarding enthalpy and free energy, as the microparticles aggregate, the total surface area is reduced. This reduction causes the net surface free energy to decrease, releasing an imperceptible and negligible amount of heat into the system. Second, flocculation operates under kinetic control rather than traditional thermodynamic equilibrium. It is a rate-limiting transport process governed by particle collision frequencies, which occur via 2 mechanisms: parakinetic, driven by thermal Brownian motion, orthokinetic, driven by induced fluid shear gradients from the pedals. Because of this kinetic dependency, true equilibrium is achieved as a dynamic steady-state limit, where the rate of flock growth is exactly equal to the rate of flock breakage. Rate of growth is equal to rate of breakage. Finally, let us consider the impacts of operating conditions. For temperature has a significant effect. Colder water exhibits higher dynamic viscosity. Because fluid shear stress correlates directly with viscosity, colder water applies a large disruptive shear force to the flocks, making them more prone to breakage. Pressure. Conversely, pressure has no effect on the process. Flocculation remains entirely unaffected by standard planned pressure changes. This is because the water phase behaves as an incompressible liquid, and the physical aggregation steps yield a net volume change of 0.
I will present about reverse osmosis desalination. The purpose of this process is to remove salt and other dissolved minerals from seawater or brackish water to produce fresh water. The main technology is a membrane-based system. We apply a pressure higher than the natural osmotic pressure, so water is forced through a semi-permeable membrane. Pure water passes through, while more salt, organic matter, and microorganisms are rejected. This is how we turn salty water into clean usable water. This slide shows the main process step in an RO desalination plant. Firstly, seawater intake. Seawater is drawn in and large debris is removed. Secondly, feedwater pre-treatment. The water is filtered and conditioned to protect the membranes. Thirdly, high pressure pumping. So, what we do? A pump raises the pressure above the osmotic pressure. Fourth, RO membrane separation. Under high pressure, water passes through the membranes as permeate, while concentrated brine is left behind. Then, energy recovery from brine. Device recover pressure energy from the brine to produce power consumption. Lastly, post-treatment and distribution. The permeate is adjusted, disinfected, stored and then supplied to user. So, this is the process water goes from seawater intake all the way to safe and potable water. Now, I will briefly explain the thermodynamics of reverse osmosis. First, RO is a non-spontaneous process with delta G more than 0. Naturally, water will move from fresh to salty, so we must apply external work in the form of pressure to reverse this. The process is controlled by osmotic pressure given by the Van Hoff equation. As pure water is removed, the brine becomes more concentrated. Its osmotic pressure increases and eventually it can match the applied pressure. At that point, there's no net water flow, which set a limit on how much water we can recover. Finally, we will explain about operating conditions. Increasing pressure increases the driving force of water flux, but also energy use. Then, increasing temperature lowers water viscosity and can raise flux, but also increases osmotic pressure and affect membrane properties. In summary, RO desalination needs energy input and its performance depends strongly on pressure, temperature and the osmotic pressure of the solution.
Treatment system, thermodynamics play a huge role in making processes efficient and safe. It helps engineers determine the minimum energy needed to desalinate water, like in reverse osmosis, so systems are not wasteful or unrealistic. Thermodynamics also sets limits for water recovery, balancing how much water we can reclaim without damaging membranes or increasing maintenance costs. When it comes to chemical reaction, Gibbs free energy help predict how much reagent is needed to remove contaminants safely, ensuring we don't overdose or underdose chemicals. Lastly, thermodynamics keeps operations safe by predicting temperature and pressure boundaries. This prevents equipment failure, especially in high pressure and high temperature systems. What did we learn in this project? We learned that thermodynamics is not just a theory, it's something we see in real industrial processes. In water treatment, it defines energy limits, reaction feasibility and recovery boundaries, helping systems run efficiently and safely. We also discovered that equations like Gibbs free energy, entropy and phase equilibrium constant have a real-life application that can even save lives by ensuring clean, safe water. Overall, this project shows that solving global water challenges means applying thermodynamic principles wisely, designing systems that are both efficient and sustainable.